Evening, everyone. I welcome you all to the live session 11 of this NPTEL course. Yeah, mic is okay. So I think we can start the session now. So okay. So good evening, everyone. Once again, welcome you all to this live session 11 of NPTEL course Non-Conventional Energy Resources. This is live session 11. The course instructor is Professor Pratap Haridas. He's professor from IIT Madras, and I am Rohit, and the PMR scholar at IIT Bombay, and I will be taking this live session. So, as per usual live session, this live session will also consist of some questions from non-graded part of the assignment, also some questions from graded part of the assignment. Apart from that, we will also discuss the concepts that are related to this graded and ungraded part of the assignment. So you all are actually welcome to this to have an interaction with me. Please question if you have any doubts or anything you want to ask. Please don't hesitate to ask me. Okay. So I think now we can start the session. So first question is, an SOFC operates at approximately 70 degrees Celsius. So SOFC, basically SOFC is or I think here I have written solid oxide fuel cell. Okay, so this is SOFC, short form is SOFC. Operates at approximately 70 degrees Celsius. No, SOFC don't operate at this temperature. This is quite low temperature for an operation of SOFC cell. Generally cells, like I think I don't remember, but maybe PEM or something that operates nearby 100 degrees Celsius or 80 degrees Celsius. So if they generally have higher operating rate temperature, more than or greater than 800 degrees Celsius. Okay, 800, 900,000 also. 1000 is quite good for SOFC fuel cell. Okay. So this statement is actually a false statement. So okay, so whenever you have any doubt about the operating temperature of this SOFC, so yeah, it is quite higher side. So one thing is that when you focus on this question, okay, so there is a concept solid oxide fuel cell. So most of you have gone through the who have gone through the weekly lectures have this concept clear, like what can be SOFC cell or PM cell or many other cells. Okay, so on similar lines, we also have different other fuel cells that are in operation, but generally these SOFC cells and PEM cells are quite famous. Quite a lot of research is going on in these type of cells. Why? Because these cells are actually SOFC cell is basically think of replacing uh, so various type of batteries to produce currents, and also PEM cells are majorly thought of replacing the IC engines in transport vehicles like cars basically. So these are much cleaner. They don't produce uh, emissions like we have in combustion. Okay, so these cells are quite good in nature. When I'm saying quite good, so in terms of performance, efficiency, environmental terms, that's what I am saying. Okay, so don't confuse it with like some other thing or so in various slides I've added 3 to 4 slides for SOFC like solid oxide fuel cell. So we'll go into detail and see what are the solid oxide fuel cell, and we'll study about the characteristics and other important parameters related to solid oxide fuel cell. So here I have added a diagram for the operation of solid oxide fuel cell. So if you clearly view this diagram, I want you guys to please have a look at this diagram for 2-3 minutes, okay? So that you can understand the basics of this diagram. This diagram is very important when you talk about solid oxide fuel cell. So if you could understand the working, the principle behind the different components of solid oxide fuel cell, you could easily get a good grasp of knowledge that can be applied to build a solid oxide fuel cell, okay? And in between, let me see if someone wants to join. Okay, no one wants to join. So since like this is penultimate session of live session, so people are more focused on exams now, okay? So please have a look at this diagram, then I will explain each and every component of it, okay? And I will also tell you that how this solid oxide fuel cell or any cell, I think it's not good to discuss the basic difference between this ICE engine and this solid oxide fuel cell, but we can have a look at this and try to make some inference about the difference between these two, working of these two different types of components. So okay, so let's see how this operates. So let us take basically what's the difference between PEM, protein exchange membrane, and SOFC. So PEM generally takes hydrogen as a fuel, pure hydrogen, whereas SOFC can take hydrocarbon as a fuel. This is the major difference between these two, and this is because of taking hydrogen as a fuel. These are much more compact than SOFC. Okay, so these can be fitted in vehicles, can be used for providing the necessary current to drive the vehicle. Okay, so we take a hydrocarbon that is methane here, which is basically a natural gas. So what do we do here? We reform methane. Okay, so how do we do reforming? So there is a water gas shift reaction or different type of reforming use by using water. So like if we have one of the water gas shift reaction that is used for reforming is I'm writing here, okay? So what it does, it converts the CO to CO2, and on the other H2 is reduced to hydrogen, okay? So what does it do? This hydrogen or CO can be fed to this electrode. This is basically anode and this is cathode. And from the other side, the oxygen can enter the cathode. At cathode, the excess electron is actually captured by the oxygen atoms, and oxygen atoms are actually converted to O2 minus. So when these O2 minus ions travel through this electrolyte, so this electrolyte is basically made up of ceramic. Okay, it's not a common type of electrolyte, it's a ceramic. So these O2 ions actually travel through this electrolyte and reaches the anode where it reacts with the hydrogen or CO2 or different atoms and a redox reaction takes place which generates free electrons. These free electrons are taken out through external circuit, which is basically the flow of current that we see from a solid oxide fuel cell. So this is the main working of the solid oxide fuel cell. So if you want to have a good understanding of this solid oxide fuel cell, then you have to basically look into the various major components that are cathode, anode, electrolyte, how reforming takes place, intake of oxygen, flow of current. These things are very much common that can be utilized for building or getting a current from a solid oxide fuel cell. Okay, so I'm sure that you must have got a good understanding through this diagram. So I've taken this diagram purposefully so that you guys can have a good sense about this solid oxide fuel cell. So in the next slide I put a video also, so you guys can have a good understanding about the working of fuel cell. So before that, let me check if anyone wants to join this session. Okay, no. Okay, no one wants to join the session. Okay, so I think we can move to the video then. So I don't know whether sound can be played or not. So if there are no sounds, please inform me. So here's the video. It's a small video that explains basically different anode, cathode, and this electrolyte in between. So we'll first see the video, then we will pause the video and I will explain each and everything here. Okay. So video is over. Okay. So let's. So this is cathode. This is the ceramic electrolyte which we talked in the previous slide. This is anode. Okay. So what happens? This is the hydrogen atoms coming at the node, as we see in the previous hydrogen atom coming at the node and oxygen entering from the cathode side. So here hydrogen atoms are entering. Here you will see the oxygen atoms are entering. And also when the hydrogen atoms are entering, it is giving electrons which flows through the circuit and it is captured by the oxygen. See, the oxygen atoms are taking up the two electrons each atom, then it travels through the ceramic membrane, then it goes to a node and the redox reaction takes place, and the electrons which are actually taken out from the oxygen atoms or the reaction chemical reaction, it flows through the external circuit as a form of current. Okay, moving to the next slide. Okay, so basically I've taken some theory portion also for the solid oxide fuel cell. So basic structure of solid oxide fuel cell consists of solid electrolyte that is usually a ceramic positioned between anode and cathode, as you have seen. Fuel is delivered to the anode, that is in the form of hydrocarbons or hydrogen, and oxygen, typically air, is delivered at the cathode. The electrolyte conducts the oxygen atom formed by the electrochemical reduction of molecular oxygen from the cathode side to the anode side of the SOFC. The fuel reacts catalytically with the oxygen ions, okay, as you have seen at the anode, releasing electrons as you can see in the previous video, data transported through the external circuit producing electricity. Okay, so I'm sure that you guys have got a good understanding about this solid oxide fuel cell. So if there are any questions, please ask. Okay, so if there are no queries as I've seen in the white box, so yeah, So we can move to the next question then. So the next question, if we think of the next question basically ask about under constant current mode of operation, the degradation of fuel cell. This is the main concept, degradation of the fuel cell. What is degradation? What can we term as degradation of fuel cell? Okay, may be expressed in milliampere per hour. So this is basically a false statement. Okay, why it is not expressed in milliampere per hour? It's expressed in millivolt per hour. Okay, all the losses, degradation, etc. are expressed in terms of volt, not in ampere. Okay, so main thing is that we need to look into what can we term as a degradation of fuel cell. So let's see. Fuel cell degradation. Okay, so fuel cell degradation is an important factor in the design of fuel cell power supply. Okay, so whenever we design a fuel cell, so fuel cell degradation is quite important. So whenever you try to understand the concept of fuel cell degradation, so it's quite a important to understand the degradation, so to design a fuel cell that can supply a required amount of power, because if you don't take degradation into account, so what happens after after a certain period of time, the fuel cell won't be able to sustain the voltage for which it has been designed, or it won't be able to provide the current that is required for the fuel cell. Okay, second thing is that if fuel cell degradation is impacted by operating condition. Okay, so this is quite a good statement or impactful statement. Okay, because operating conditions, what can be the different operating conditions for fuel cell? So one thing is that key, the voltage is an important criteria here. Let me guess. The voltage is an important criteria here. Operating voltage, at what voltage it is operating, the temperature, humidity also impact. Okay, voltage oscillations. So these are basically major operating conditions that impact the fuel cell degradation. Okay, another thing is that key polarization curves provide information on the performance losses of the fuel cell under operating conditions. So if you have to know the losses, different type of losses related to fuel cell, then polarization curves are basically quite an important terminology when you want to discuss this type of performance losses. Okay, so how does this polarization curve look like? And we'll see about this polarization curve in upcoming slides. Okay, so this is the example of a polarization curve from a fuel cell. So I have taken this figure from the lecture slides. You can refer it from there also. So see, we have voltage on y-axis and current density, that is ampere per centimeter square, the basically stack area. So as the current density increased, we see that there has been a drop in voltage. Okay, so for example, there has been a current density of 0.4 ampere per centimeter square at the 0.5 volt. Okay, so if there are 200 cells are stacked in series, so how much current they can provide? So just multiply 0.5 into 200, which is actually equal to, and if you want to determine the current, so this is basically current density, so just multiply the 0.4 ampere per second square, centimeter square, sorry, my mistake, into how much is the area? 100 square centimeter. That's 40 ampere. Okay, so okay, now in the next slide, we'll discuss about these various losses. One loss is here, one loss is here, one loss is here. What are these losses? So okay, so if we see the curve, okay, so there has been quite decrease in the voltage as we increase the current density. So here it has if this is the operating open circuit voltage, we have studied this open circuit voltage when we are discussing the solar photovoltaic cells also. So voltage loss due to mixed potential and crossover. Okay, so and this is the region of activation polarization, also known as activation loss. And this is basically ohmic polarization or ohmic loss. That is basically loss due to resistance, ohmic losses. This is region of concentration, polarization, or mass transfer loss. Okay, so there are three type of losses that actually reduce the voltage, that is ideal voltage, and total voltage loss. So we get the exact voltage somewhere here. Okay, so and this is basically voltage loss causing mixed potential and crossover. Okay, so these two were actually quite important concept about fuel cell degradation. So please look into it, and if there are any queries, please ask. Okay, till then let me see also if somebody wants to join. Okay, no one wants to join. Please have a look. So if there are no queries, then I think we should move to question 3 now. Okay, so yeah, seems like there are no queries. Let me see. No. So yeah, let's move to question 3. So basically, question 3 talks about that key. Let me check if there are any issues. Oh, there are no issues regarding. So question 3 talks is that key there are two fuel cells. Okay, each has the operating voltage of 0.6 volt and the current density is zero point 0.5 ampere per centimeter square are connected in series. Okay, so these are connected in series. The area of each of the cell is 30 centimeter square. The voltage of the stack is okay. So stack voltage is basically the voltage of cell multiplied with number of cells. So we have voltage of single cell as 0.6 volt, and if there are two cells that are attached in series, then we have to multiply it with number of cell, that is 2. So voltage of cell is this and number of cell is this. So this is equal to 1.2 volt. So the correct answer will be 1.2 volt. So this is basically please note down this formula. This can be utilized in the final exam also. This type of questions can be asked in final exam. So you have to think carefully when you try to answer these questions in final exam. Okay. So just focus on the question. The questions are quite straightforward, quite uh, formula based. So when you try to get these type of questions, so just read the question, what are the data given, which formula can be applied to this question, and then you can apply this question and get the answer. Okay, so I don't think these type of questions will be very difficult to answer in final exam. You can easily score marks in these type of questions. So also I have given a formula for different level. You can note down this formula for uh, final exam. But apart from that, I just wanted to ask. Let me give you another question, okay? And let me see that if you guys can do it. Not. So let's say three fuel cells are there. Each are stacked. Each one are of point 0.5, point 0.5, point 0.5. Okay, and so what is the stack voltage that we can get from here? So please apply your mind and get the answer. Okay, please think. So so our formula is given here. You just have to apply the formula. So what is the V cell? V cell is zero point 0.5 volt. And what are the number of cell? So it's 3. So just you have to put zero point 0.5 is the potential of cell into number of cell, that is equal to 1.5 volt. So this is the voltage of stack that you are going to get. So we'll have different type of question based on this type of formula, and we'll see in further slides also. Also, I think a question has been there is there from grade part of the assignment, so we'll look into that also. So you guys will be able to answer those type of questions very clearly and very concisely. Okay, please look into this. This is very important. Let me mark this slide as important. Okay, this is very important. So it says the fuel cell stack size. So the first step in engineering a fuel cell stack is to obtain the power requirement. How much power you want from that fuel cell? Okay. So the stack is then designed to meet those requirements, and the maximum power, voltage, and currents are often known. The power output of a fuel cell stack is product of stack voltage and current. That is, you already know P equal to V into I. That is voltage into, this is voltage, this is current. Okay, so this is power that is to be obtained from fuel cell, voltage into current. Okay, so the maximum power and voltage requirement are dependent upon the application. What are the different types of application that you want to be conducted through the fuel cell? So it's very much depend on the type of application. The engineer must understand these specifications to build an appropriately sized fuel cell stack. It is helpful to know the current power and density when designing a fuel cell stack. These are often unavailable initially but can be calculated from the desired power output, stack voltage, efficiency, and volume and weight limitation. The current is a product of current density and cell active area. So if you want to know the current, okay, and that is to be filled here. So you know the current density of the fuel cell. Like in the previous slide, we have given a current density of 0.5 ampere per centimeter square. So it can be multiplied with the area of fuel cell to get the actual amount of current. The cell potential and current density are related by the polarization curve as we have seen in the previous slides. So cell potential is a function of basically the current density. So if you know the current density, you can know the current from the polarization curve. So through this voltage and current, you can obtain the amount of power that is required for the fuel cell stack. And so an example of polarization curve, we have actually seen the polarization curve here. Okay, polarization curve here. And the efficiency of the fuel cell is basically voltage of the cell divided by 1.482. Okay, so you can remember this formula also to calculate the efficiency of the stack of the fuel cell. So he is specific that this is efficiency of the stack. Okay, so if you know the voltage from the fuel cell divided by 1.482, you can get the efficiency. So this is very important slide. Please have a thorough look at this slide and please ask any questions if you have any. If you want to um, apply these concepts to your numerical. So there can be various amount of numerical combining these concepts that can be asked in the exam. So just don't be fearful of the numericals or any, don't panic. Just apply your mind, just use the concept that are being taught in the lectures by professor himself. You can easily solve those numericals. Just you have to understand where you can get these values. That's all. Okay, so I think I will leave you guys with this slide for some time, so you guys can actually look into it and think what can be done to actually what are the concepts that can be that is needed to be understood. So partial oxidation used for reforming fuels is an exothermic process. So we move to the next question if you don't have any doubt. So yeah, partial oxidation. So here the question basically is talking about partial oxidation. So used for reforming fuels. So you know the reforming fuels, I have discussed a reaction, water gas separation. So there can be various n number of reactions that can be used for reforming fuels. So generally fuels are reformed to produce hydrogen. Okay, a typical case it can be reformed for anything. So is an exothermic process. So this is quite a true statement. So why true? Because in most of the cases, almost 99% of cases, partial oxidation is an exothermic reaction. But there is a fuel whose partial oxidation is actually endothermic. So we'll talk about this concept also. But for this is quite a true statement. Okay. So if we see the partial oxidation generally occurs when oxygen fed at a level below that is needed for complete oxidation. So if we have, let's say we have alkane or hydrocarbon. So what happens? We give it oxygen and CO2 plus H2O is formed. So we give enough amount of oxygen, so the products are CO2 and H2O which are formed due to the oxidation of CH4. But what happens? The oxygen will limit the quantity of oxygen. Okay, let's say we give only zero point 0.5 oxygen. So in that case, we'll basically have a CO because not enough oxygen is present in the reaction to complete and to form CO2. There will be some formation of CO2 also plus H2O plus some other gases can be depending on whether it is air or pure oxygen. Okay, so this is basically partial oxidation. So we require 1 mole of oxygen, but we are providing only zero point 0.5 or zero point 0.4, zero point 0.2, zero point 0.3. Okay, so this is basically partial oxidation. Generally produce hydrogen and carbon monoxide. Hydrogen is also produced. Okay, why? There cannot be enough oxygen to produce water. Okay, so another thing is that methanol cannot be partially oxidized. Both the fuels consider the partial oxidation of ethanol is the only reaction that is endothermic. Okay, so we were earlier talking about this exothermic thing. Yeah, 99% of the 99.9% of the cases this partial oxidation is exothermic, but in case of ethanol, this can be endothermic. Okay, so we have this. I put a diagram because diagrams are very important to make the concepts clear and to make a elaborative illustrative way to understand the concept. Okay, so this talks about catalytic partial oxidation. See, partial oxidation is something, some type of reaction, or is a type of reaction that doesn't generally require catalyst. But here we talk about catalytic partial oxidation. The picture is as such. So we give hydrocarbon here, so it is oxidized, so it can form ideal syngas. Syngas is basically CO plus H2 plus other gases. Okay, and due to this syngas, we can use it to produce methanol, or we can use Fischer-Tropsch to produce different type of fuels. We can also reform it to produce hydrogen also. We can oxidize the CO and get the hydrogen out of it. Okay, so that can be utilized in fuel cell and different other processes. So the partial oxidation is quite important process. Generally, I will suggest you guys to read about this term or this process, uh, gasification. It's a very important chemical thermochemical process that can be utilized to produce hydrogen. Okay, so we are moving to the last question. Till then, I will suggest you guys to please have a look at this concept partial oxidation. And if there are any queries, please write it down, or you can unmute yourself and ask in between the session also. Okay. So basically, gasification is a combination of different processes. So as to gasify fuel, so fuel can be biomass or biomass can also be used as a fuel. And on similar terms, there can be okay. So it can be used for gasification. So there can be different things also that can be. So one thing that key methanol cannot be partially oxidized of the fuels consider the partial oxidation of ethanol is the only reaction that is determined that we discussed in the um, uh, previous 2-3 minutes also. So I want you guys to please read about the topic gasification. So because I will give you a brief about this topic gasification. So it is basically used to gasify any fuel. So that fuel can be biomass also. So what we do, we feed the biomass to so we have this gasifier. So it's a downdraft gasifier. This is fuel. This is air that goes into the same direction. So what happens? There are different zones. Like there are reduction zone, oxidation zone, that is combustion zone, partial oxidation zone here. Okay, drying zone here. So different zones. So one of the zone here is partial oxidation, where this hydrogen and carbon monoxide as a fuel is produced here. Okay, so this is basically the product of this process is actually process gas known as syngas. So syngas is basically CO. Okay, so it's basically syngas that can be utilized for different other chemical reactions to extract the hydrogen from this. Hydrogen is actually a fuel. The CO is also a fuel that can be utilized in various processes. Okay, so please read about this gasification. Then we will have a discussion in the next class. ठीक है. Okay, so moving to the next question now. Uh, we have this theoretical potential voltage of a fuel cell is 1.23, and the operating point of the fuel cell is operating basically voltage is zero point 0.6. The overpotential losses are, so as we have seen here, like here, so this is ideal voltage, theoretical voltage, and this is actually the uh, voltage which is after losses. So this can be calculated by dividing this 1.23 minus zero point 0.6, that is 0.63 volt. So the correct answer is 0.63 volt. Okay, so you guys please focus on this and try to see if there are anything you want to ask. Okay, so we have to. This is the penultimate question of today's session. So there are three losses, and the regions are mentioned. So we have to match these. Okay. So the correct answer is activation losses are basically reaction site has become bad. So due to that, activation site losses are there. Activation losses are there. Ohmic losses because conductivity has decreased. Okay. And when most mass transport losses are basically pathway for reactants is blocked. So because of these three the regions, the three losses are there in the fuel cells. Now the last question of this session: if the cell with given specification at assembled in series, how many cells, how much area would be required for 1 kilowatt power? So we know power equal to V into I. Okay. So if it's 1 kilowatt, then sorry, 1000 watt equal to zero point 0.5 into N into 0.2 into area. Okay, so there can be various combination of N and A. So for this, 100 cells with 100 square centimeter area will also work, or either you can use 200 cells with 50 square centimeter area. Okay, so these two options A and C both are correct here. So okay, so this was the last slide, and thank you for attending this session. We'll be finishing this session today, and we'll meet for our last session of live session on next Tuesday. Till then, if you have any questions, please find me at this email ID. You can write an email to me, but I will suggest you ask these questions in the discussion forum of the NPTEL. Okay. So, okay. Thank you once again for attending this session. We'll meet on the next Tuesday.